Good morning to all of you. I, A. Satyanarayan Reddy. While launching our course Linear Algebra, I began by sharing the syllabus, which I designed as an infographic using AI tool called Notebook LM. As we progressed through the first core section, solving system of equation that I described here, I have supported the lessons with several short explanatory videos, also created using AI tools. At that moment, we saw those videos in a relaxed way. Now its speed is increased. Now, to bring this foundational topic together, I have compiled a summary reel of those videos. This will serve as a quick, cohesive review of the key methods and concepts we have covered so far. Here is a recap. I hope find this helpful and considering your understanding. Thank you.
Have you ever wondered what happens when you take a single point and multiply it by different numbers? Let me show you something fascinating about scalar multiples in mathematics. Pick any point in two-dimensional space. Let's say the point 2, 3. Now multiply this point by different scalar values. When you multiply by 2, you get 4, 6. Multiply by 3, you get 6, 9. Try negative values like 1, you get short 2, 3. What about fractions like 0.5? You get 1, 1.5. Here's the incredible pattern that emerges. All these points form a perfectly straight line passing through the origin. The original point, all its scalar multiples, and origin, 0 Sauro, all lie on this same line. This line extends infinitely in both directions. When you multiply by positive scalars, points move further from origin in the same direction. Negative scalars flip the point to the opposite side of origin. Scalars between 0 and 1 bring the point closer to origin. This beautiful geometric relationship shows how algebra and geometry connect. Every point in the plane defines its own unique line through the origin. This is the foundation of vector spaces and linear algebra. Mathematics reveals patterns everywhere once you know where to look.
Let's explore lines in two dimensions. Consider a point AB on the coordinate plane, excluding the origin. So AB is in r squared minus the origin. Our task is to find the equation of the line passing through the origin and the point AB. The equation of this line is 9bx plus ay equals 0. Now, let's find a point that does not lie on this line. Consider the point minus ba. Why doesn't it lie on the line?
All right, let's talk about an equation you've probably seen a million times. ax equals b. Looks super simple, right? Well, today we're going to see that this little equation has some serious tricks up its sleeve. The answer is not always what you think it is. So, really, how many answers can an equation this simple actually have? I mean, seriously. If you're thinking, one, obviously, then stick around because your mind is about to be a little bit blown. It gets way cooler than just one. And this right here, this logic map is going to be our guide through this whole thing. It literally holds every single possible answer. It's kind of like one of those choose your own adventure books, but for math. It makes sure we ask the right questions at the right time to get to the real truth. Okay, so just to make sure we're all on the same page, our mission today is to find x in the equation ax equals b. That's it. A and b could be any numbers, and our job, together, is to figure out what x has to be. So, the map starts us off at a major crossroads. The very first question we have to answer is a not equal to 0? And believe me, everything, hinges on this one question. Yes or no? That one answer sends us down two completely different paths. Okay, let's take the easy road first, right? The one we all remember from school. We're going to follow the yes path. So for now, let's just assume a is any number in the universe, as long as it's not 0. And boom, look at that. The flowchart points us straight to one single beautiful answer. The solution is just b divided by a. It's that simple. Direct, clean, no fuss. This is always the case as long as a isn't 0. Now, you see that s and the curly brackets, right? All that means is solution set. It's just a fancy way of saying, here's the collection of all the possible answers. And in this case, the only thing in our little collection is b/a. That's it. One value, one solution. Done. Let's make this real. Say you have 2x equals 10. Well, a is 2, b is 10. You just plug them in. The solution set is 10 over 2, which is just 5. That means the only number on the entire planet that works for x is 5. See? One equation, one answer. Nice and tidy. Okay, but that was the superhighway, the easy route. Let's rewind. Go all the way back to that first fork in the road. What happens if a is 0? Now, this is where our map becomes a lifesaver, because this is where the real adventure begins. So we take the no path, and we hit another checkpoint. The map forces us to ask a second question. It's like, okay, we know a is 0, got it. But what about b? Is b something other than 0? And again, our whole journey depends on that yes or no. Let's say yes to this question. So this is the first weird scenario. A is 0, but b is, well, it's not 0. Let's say it's 7. So our equation is now 0 times x equals 7. Just let that sink in for a second. 0 times something equals 7. Does that even make sense? And our math gives us the answer loud and clear. No. Solution. It's impossible. And it makes total sense when you think about it, right? Anything times 0 is always 0. It can never equal 7. The equation is basically a lie. It's a contradiction, so there's no value for x that could ever make it true. I love this way of putting it. You just can't multiply by 0 and get something from nothing. It's a total mathematical dead end. And our map is smart enough to see that and tell us, hey, stop. Don't even bother looking for an answer here because it doesn't exist. All right, we have one last path to explore on our map. What if we go back to that second question and say no? This is the grand finale, the most mind-bending scenario of all. What happens if A is 0 and B is also 0? The equation becomes 0 times x equals 0. So, what number for x would make that true? Think about it. Following this last no path takes us to our final destination, and it's this weird-looking symbol, S equals R. So, what in the world is that? Well, it means something absolutely amazing is happening here. That funky R symbol, it just means the set of all real numbers. And what that's telling us is that when you have 0x equals 0, literally any number you can possibly think of is a solution. No, seriously, try it. What's 0 times 5? 0. What's 0 times negative a billion? 0. 0 times pi? Still 0. It works for everything. We don't have one solution, we have infinite solutions. So let's just pull back for a second. This one super simple looking equation, ax equals b, can lead to 3 totally different places. You can have exactly one solution, you can have absolutely no solution, or you can have a mind-boggling infinite number of solutions. And this table here basically boils our entire journey down into a perfect little summary. It's the master guide. Case 1, A isn't 0, you get one solution. Done. Case 2, A is 0, but B isn't. No solution. Dead end. And case 3, the wild one. Both are 0, infinite solutions. See? Every single possibility is perfectly covered. And that really gets you thinking, doesn't it? What this little flowchart does is it forces us to slow down and consider all the angles, even the weird ones we'd normally just gloss over. It's a tool for clear thinking. So how many answers can one simple equation actually have? You know, if you take something like x minus y equals 1, the answer is, well, it's infinite. But how in the world do you capture infinity in a single, neat formula? Today, we're going to crack that exact puzzle. We're talking about a surprisingly elegant method to find every single solution to equations like ax plus by equals c. Let's dive in. I mean, really think about it for a second. For x minus y equals 1, you could have x is 1, y is 0, that works, or x is 2, y is 1, or x is 100, y is 99. You could literally sit here all day just listing them out and you'd never get to the end. So the real challenge is, how do you capture every single one of those possibilities in one simple formula? That's the mission, and it's exactly what we're going to solve. Okay, so when you're faced with a puzzle that has infinite pieces, the trick is to start with a much simpler version. We're going to tackle a related but way easier part of the problem first. And trust me, this is the foundation for everything that's about to follow. So instead of trying to make our equation equal some number c, we're going to aim for an easier target first, 0. This is what's called the homogeneous version of the equation. Now, it might feel like we're taking a detour, but understanding the pattern of this 0 case, that is the absolute key to unlocking the whole puzzle. So what exactly is a homogeneous equation? It's just the fancy name for our 0 case. And the cool thing is, its solutions aren't just a random mess of points. They form this beautiful, totally predictable pattern. It's a straight line that cuts right through the origin. And that pattern, that's what we're after. And here it is, that entire pattern captured in one tidy little formula. The whole family of solutions, which we'll call S, can be generated by just taking this specific point, negative b comma a, and multiplying it by any number t you can think of. As you change t, you trace out every single solution to the ax plus by equals 0 equation. It's the complete recipe for the first part of our puzzle. All right, so we've got the pattern for the 0 case locked down. Now it's time to find the second crucial piece of the puzzle. This is where we connect our simple problem back to the one we actually want to solve. Okay, we are back to the main quest, solving for C. We've got that 0 solution pattern, our set S, sitting in our back pocket, ready to go. So what's the next move? Well, the next piece is actually surprisingly simple. Get this, we don't need to find all the solutions right away. Our only job right now is to find one, just one. Any solution that works will do. This single solution is going to act like our anchor, our starting point for everything else. And we'll give it a special name, the particular solution. And I want to be super clear here, the particular solution isn't some magical unique point. It's just any single pair of numbers that works. For our old friend x minus y equals 1, the point 1 comma 0 works. So does 2 comma 1. You just have to find one of them. And like the source says, keep that with you. It's that important. Okay, this is the big reveal. This is the moment we've been building up to. We have the pattern from the 0 case, and we have our single starting point. Now, we're going to put them together to get the complete answer. And here it is, the whole method in a simple 3-step recipe. First, you solve that 0 case to find the entire solution pattern, S. Second, you go hunting for just one single solution to the real equation. That's your anchor point, UV. And finally, for step 3, you just add them together. That's it. The entire family of infinite solutions is just your pattern S, shifted by your anchor point. The idea behind this is actually pretty cool and really intuitive. Just picture all of those zero-case solutions forming a perfect line that goes through the center of a graph. Your particular solution, that one point you found, acts like a handle. You're basically grabbing that entire infinite line of solutions and just shifting it or sliding it over to your new starting point. Every single point on that new shifted line is a correct answer to our original puzzle. Okay, theory is one thing, but let's make this concrete. Let's circle all the way back to the question from the very beginning, x minus y equals 1, and put our new 3-step method to the test. Let's see it in action. All right, let's walk through the steps. Step 1, the zero case is x minus y equals 0. That just means x has to equal y. So our solution set S is all the points that look like t comma t. Easy enough. Step 2, find one solution. A super easy one for x minus y equals 1 is the point 1 comma 0. And now for step 3, just add them up. The full solution is the set t comma t plus our starting point 1 comma 0. And when we do that final addition, we get this beautiful, simple formula. Every single possible solution to x minus y equals 1 can be written in the form t plus 1 t. This one tiny expression has captured the entire infinity of answers we were looking for at the start. How cool is that? Let's just kick the tires on this thing. Pick any number you want for t. Let's say t is 0. Well, then you get the point 1, 0. And yeah, 1 minus 0 is 1. What if t is 1? You get 2, 1. 2 minus 1 is 1. What if t is a negative number, like negative 1? You get 0, negative 1. And 0 minus negative 1 is 1. See? It works every single time, cranking out every possible solution. So, our method is fantastic when a solution actually exists. But the source material brings up one last, really important question. What happens if the equation you start with is just impossible to solve? Well, there's really only one way this can happen. It's when both a and b are 0. If that happens, your equation becomes 0 equals c. Now, if c is anything other than 0, say 0 equals 5. That's just nonsense, right? It's impossible. There is no solution to find. So what's the game plan in that situation? And I absolutely love this final piece of wisdom from the source. If you stumble upon an impossible equation, the problem isn't about finding infinite solutions because there aren't any to find. So what do? Nothing. The problem solved itself by being impossible. You can just be happy. A perfect and honestly a pretty practical way to wrap up our journey into this infinite puzzle.